Okay, so hello to everyone. So I will be presenting a paper which is basically going to the opposite direction as the York's one, and the paper will be about efficient generation of macro operators. So just, we have a lot of, let's say, planning domain models and a lot of state-of-the-art planners which are very efficient. But, sometimes we might need some additional knowledge which can help these planners to solve problems more quickly. The problem is that all these planners are somehow using PDDL, some sort of input language. And, if we want to exploit these planners without any modifications or extensions, so that you still have to have, a description in PDDL. So that if you want to really exploit that knowledge, so you have to somehow encode that knowledge into these PDDL models, so that you need to reformulate these domains and problem models. So, a lot of people are familiar with what macro operators are about. They basically encapsulate sequences of original planning operators. And because of that, they can be somehow encoded as standard operators. So they are a very, good type of these planner-independent knowledge, because these macro operators can be easily encoded into these domain models. And also what is quite nice, that if we use macros, so that we are not compromising completeness of the planning process. So, and here is the nice example from Bloxworth. So basically this is something, opposite to York's presentation, so that we have two operators, unstack and put down. And, we might do some observations, and then we will realize that, these operators are, quite commonly, in sequence. And, it might be better to merge them together to have just one macro operator, unstack, put down. So that basically we are having some sort of shortcut through the intermediate state. Yes, macros, can be understood as shortcuts in the search space, so which is quite a nice feature. But, on the other hand, so what's the shortcoming of macros? So because usually if they encapsulate a whole sequence of operators, they have a lot of arguments and they can have a lot of instances. So that it is, very, let's say, not very nice property, because we have some shortcuts, but we have a lot of these shortcuts, and we might end up in some similar situations, and planners might have problems with that, because we might, for instance, have increased memory requirements, or also processing all these instances, and where many of these instances are not very useful, so this can somehow slow down the planning process. So what we can do with this? So we can use some nice technique which is called outer entanglements. Outer entanglements are relation between planning operators and initial or goal predicates. So we have two types. We have entanglements by init and entanglements by goal. And informally said that basically for entanglement by init, we just allow instances of operators with which somehow uses predicates which are initial predicates, and similarly to entanglement by goal, we allow only instances of operators which achieve goal predicates. So we have quite a nice example of Bloxworth in here. We have an operator unstack in here, and we can observe somehow that basically we have this initial situation, and we don't have to instantiate basically that unstack operator for all the possibilities, because if we just unstack blocks from initial position, which means that we just will need two instances of this one, so that this is sufficient, because we unstack blocks, put them to the table, and then we can stack these blocks into the goal positions. And this is quite similar with stack operators, because also we don't need all these instances, but we are just happy with these two one, which will basically achieve the goal state. So, but how to use these entanglements to somehow generate more efficient macros. For this, we introduce something what is called argument matching graph. So we have some arguments which are basically nodes in that graph, and we are putting edges in between these nodes if, well, for the simple argument graph, we have a static predicate which is somehow putting these arguments together. For instance, in here, we have the lift operator from depots domain, where we have 4 arguments. One is hoist, place, crate, and surface. So we can see that there is a static predicate at hoist place, so which says that that hoist is at one place, and we can somehow make an edge here. The thing is that what it says is that we don't have that many instances, because if we don't have any information, so that we can just do a product of numbers of all these objects. But in here, if we will see that a hoist is at one place, so that we just have product of just these 3 arguments. But we might do some further observations, which are these entanglements. We can somehow observe that we are lifting the crate from its initial place, as well as we are lifting the crate from its, let's say, initial position, initial surface. So, and then we can add these 2 edges as well. And this will somehow restrict the number of instances just for a number of crates, because this is the usually highest number. And how we can use all of these? Well, we have these outer entanglements. However, the problem is that they are, let's say, intractable to this side. So we used in some of our previous work approximation method, which is somehow efficient, but if we really want to guarantee completeness, so that if we apply these entanglements to original operators, and if we are somehow unlucky, so that we might lose solvability of some of the problems. But if we only apply these entanglements to macros, this is okay, because we restrict the number of instances, and if we are unlucky and remove some useful instances of macros, then we still have original operators, so that we still can achieve the goal. And how we can use that argument matching graph with this? So this is some sort of, let's say, heuristic estimation of the number of instances of these operators. Because, as we saw in this example before, so that, basically the number of components can somehow indicate the number of instances. So where in here we have n, which is, let's say, the number of objects to the power of number of components. Because usually the observation is that the number of predicates in initial or goal state is somehow the same as number of objects. So of course there are some domains where this is not true, and such predicates can be removed from argument matching graphs. So, and one more thing is that we can directly exploit outer entanglements in the macro learning process. So here this is just a high-level algorithm for generating macros. So I would say that this is quite similar to other macro generating techniques. So we somehow reused part of our previous work for generating candidates for macros, where we in our previous work, where we analyzed dependencies and independencies between action in training plans. And from this, we were somehow able to find actions which are or can be adjacent in training plans, and what arguments they share, and so on. So this was basically reused. But then we came with, let's say, different technique how to rank the candidates. What candidate is the best one, so and so on. Because we would like to generate efficient macros. So, and in here, basically, we would like to prefer these candidates which are somehow related to these entanglement relations, because we say that we have that entanglement by init, which should be something like we are starting with, so that if the first operator has that entanglement relation, so it's nice. And of course the second operator, which is going to be merged into the macro, so that it is nice if that operator achieves some goal predicate, so that if it has some entanglements of goal and so on. Then we can somehow do some other check to say whether the candidate is somehow promising, which means that there are also some, and I will show you example after that, that macro should be, for instance, somehow informative, because it might happen that, for instance, you can put together two inverse operators, and then the result is basically something which doesn't do anything and so on, or for instance the number of instances is very high and so on. So then if we generate some macro, we can update training plans and then go again for the step number 1 until we don't generate any macro, or we reach the limit of macros to be generated. And after that, we have some additional filtering techniques to prune some unpromising macros. So for the example, we took the gripper domain, the IPC7 version, which is basically extended version of the IPC1 or 2 gripper domain by having more rooms, and objects are putting randomly in these rooms, and also the goal is to somehow move them into some other rooms. So we have these 3 operators. And these numbers are the number of components of simple argument matching graph, because these are original, so we are not applying entanglements on them, because we want to perceive completeness. So then we select operators pick and drop, because pick is somehow picking something from initial position, and drop is putting something on goal position. But if we put these together, so that these are inverse, and then the result is uninformative, because basically we don't do anything in total. So then we move to the next one, which is move drop. It is selected because still we have the number of components. In here we are taking into account entanglements, and this is not worse than the number of components of the original operators. So then we move on and select pick move drop, which is quite nice, because we are putting the object in the initial position, then move to the goal position and drop it there. And taking into account in all these entanglements, so the number of components is very low. Then we can generate some other and more complicated macros, and still the number of components is not that high, but also not that nice as this one. So which means that in the final filtering stage, these long macros are filtered out. So then we have to somehow decide whether keep move drop or pick move drop. But because pick move drop is nicer, because it has only 2 components of argument matching graph, and which means not many instances, so we decide to keep this one and filter out that move drop. So we did our experiments to all the domains from the IPC7 learning track. We selected 5 state-of-the-art planners, which are, very good performing and based on different techniques. Then for learning, we used 5 to 8 simpler problems to generate training plans. It was usually dependent on the number of operators in the domain and so on. Then basically for every planner learns for itself, so that every planner generated a set of macros just for itself. And we observed that usually macros were quite short, that it were of length of 2 or 3, but in some occasional places, situations, so we have longer macros as well. And here are the results. So we compared our technique with the original encoding and the other macro generating technique, Wizard, which is from Hacking Newton, and guys from right now from King's College. And we got, as you can see, quite nice results because we increase coverage. We also have in many times the problem was solved in the smallest time, and also we used IPC score. There is basically one exception, which is LPG, that only for LPG case we were worse. Still better than Wizard, but worse in general. But for instance, for Llama, we were much better because this is quite a huge improvement. So that very likely the problem is that LPG is based on local search, and even small increase of branching factor might lead to some additional overheads. The thing is that these results are cumulative, so which means that in some domains, so we got really impressive results. For instance, in that gripper domain, because that macro which I showed is very useful. So. And right now to conclude, so that we presented MAM, a method for generating macro operators, which exploit outer entanglements, which are used to somehow limit the number of instances. So, and we empirically demonstrated that it works well, so that we were able to improve the process, even given the state-of-the-art planners, which are usually good performing. And also we compared against some other technique and Wizard, which we also outperformed. So there are some, let's say, possibilities for future work. Because recently there was work published by Al-Hosseini and Beck on SARA, and they are learning problem-specific macros. So because we are learning domain-specific macros, and they demonstrated that in some cases it is better if you have problem-specific macros, because these can be exploited in a better way. And of course, because our implementation right now only support typed strips, so that we would like to extend it in future to support ADL features, and possibly for some durative actions and some other things, because they are quite important also for, let's say, real-world applications. So okay, thank you.
So macros and splits, that seems like a very interesting result. What will happen if we combine them, in your opinion? Let's say that we take the macros and then apply Jörg's technique on that. Would we get the same thing? Would we get changes?
Yeah, that might be interesting. And we had a discussion about, 2 days ago about this. So because yes, this is somehow going into the opposite direction, but right now it is just guessing what will happen. So if we generate macro and then apply your technique to just split it out, or if the result will be somehow different. So, but yeah, it is. And it, yeah.
You can get a longer macro, and then basically when you partition it, you can get different lines
yeah.
between the actions and the virtual domain. So yes, you could do something different, whether that will be useful with anybody's.
I think that the best thing would be to identify areas in the plan where you can apply this or that. I guess that's your next. It's like ICAPS 15 paper.
Well, might be.
So how about the other way? I mean, my intuition would be that by splitting and then applying your macro stuff would be better, because you reduce the number of possible actions, right?
Yeah, but I mean, then maybe in that case it might be quite tricky with completeness, because right now we are basically leaving the original operators as they are. So if we somehow split them, then put them together with entanglements, so that we might end up in situation then we could apply these entanglements for the original ones at first. So which is also usually very useful. But if we really want to keep completeness, so that this might be a problem.
Okay.
So I don't know about the details of the technique. I mean, sorry to give a separate answer. I don't know about these entanglements a priori. If you first split and then do macros within the split, then you get something that you could have produced just by split in the first place. So you don't actually get something new. According to our techniques, maybe it's entanglement.
Yeah, maybe we can we can check.
More questions? I have a question. So I was wondering if you could comment on what makes a good training set for the plans that you're using to learn the macros. Have you played with that at all, or have any intuition about what makes a good training set?
Well, I mean, it usually depends on how, let's say, complex the domain model is. But usually, if we have some training set of 5-6 plants where the length of the plants is something like from 30 to 80 actions, so that it is fine. The thing is that sometimes in these training problems, and if we use some planners and we are using suboptimal planners, so which sometimes the quality of the plan is not very nice, and it might prevent to extract some macros, because what is not said in here, and it is said in the paper, that for some planners we were not able to extract, for instance, some macros in blocks world. I think in Probe it was quite nice, because Probe gave us a good quality plants for training. But if we don't have them, so that then it is quite messy.
One quick question.
Have you looked at learning macros specifically for a given heuristic?
Well, there are some approaches, but we want it to be planner independent, so that I mean, right now it is more in general. But
I wasn't meaning for a specific heuristic, but sort of like you have problem-specific heuristics, that get tailored to a problem. Having macros that are tailored for, so you have a general technique for tailoring the macro to any heuristic that you're given, or any class, a given class of heuristics.
well, I mean that this method is not let's say very heuristic specific. So I mean that probably it might be somehow achieved if we use, for instance, different parameters for learning. Because I mean, for instance, as we shown for LPG case, so that this is not very nice. On the other hand, I mean, Wizard is more, let's say, tailored for planners, because it uses some genetic algorithms which are somehow, let's say, cross-validated these macros and so on. So that we are not cross-validating these macros, so that we have some, let's say, general insights what we somehow consider as a good macro and as a bad macro. And well, we demonstrated that it works in general case. But I mean, of course, if we, for instance, introduce some other arguments which will be tailored to some specific planning technique, so that's very likely we can get some better results.
Okay, let's thank our speaker again.